Okay, so let's do a practice problem here. So let's take my pen. Let's take silver nitrate and add it to, let's say, calcium phosphate. All right, so this is a type of problem I'll have you do an exam. Fill out finish the molecular equation, do the complete ionic equation, and then do the net ionic equation. And balance just the net ionic equation. If you want to balance all the other ones, I'm fine with that. But for right now, you just have to balance the complete ionic equation. All right. So I'll give you guys a little time to work on that. All right. Looks like most people are done. Half the group. I'll give you guys a few more minutes. All right, let's start going over this. All right, so like I told you last week, I like to do the complete ionic first just to kind of know what ions I have for each of them. So the silver nitrate will be broken down into a silver ion plus a nitrate ion. And then the calcium phosphate, calcium, remember, has a 2+ charge. And then the phosphate has a 3- charge. Remember, these numbers don't come down because that's how many of the Ca pluses I have. Now, if you want to balance it, you could put a 3 here, and you could have a 2 there. That's where the 3s and the 2s go. It's the balancing, but it's not in the actual ion itself. All right? So the silver is going to pair up with the phosphate to give me Ag3PO4. And that is going to be a solid, if you look at the solubility chart. And then calcium nitrate, Ca3,2, that's going to be aqueous, because it has a nitrate. So in your net ionic equation, your complete ionic equation, you have Ag3PO4 as your solid, and then you have calcium ions, and you have nitrate ions. So those are still, I couldn't write over here because I have the chat box right in front of me. Okay, so what are the spectator ions? Remember, the spectator ions are the ones that don't change. So calcium 2+, calcium 2+, it stays ionic. Those is a spectator. Nitrate is a spectator. So whatever's left over, so the silver plus the phosphate, they come together to form the solid silver phosphate, and this should be, you should balance this, so you'll have a 3 here. If you want to put a solid, that's fine. Okay. Now, I always get this question every year. I haven't heard it yet from you guys, but in case you're wondering. There's a lot of people say, do I need to put an AQ here? If you want to, that's fine. It's kind of obvious. Since it's already, it's still in the ionic form, it's still technically aqueous. So you don't really have to do that. But if you do, that's fine. If you want to make it complete, that's fine. Okay, any questions? That's the precipitation reactions. All right, so here's a double replacement, just going back through it. We also learned a second type of double replacement reaction, which was the acid-base neutralization reaction. So here was the neutralization. So as far as this reaction, double replacement, there are 2 types. One is the precipitation. So remember that PPT is precipitation. The second one is neutralization, or acid-base. All right, acid-base neutralization, or acid-base. So here's an example. You have a base right here, the magnesium hydroxide, adding it to the acid, and it neutralizes. You get water and salt at the end. All right, and your net ionic equation usually becomes H plus OH minus, gives you H2O. In this case, it's a little different, but That's pretty much, notice you have the H plus and the hydroxide. So that's the other type. Okay, so let's talk about now oxidation, redox reactions. These can get a little complicated. Let me just open up my notes real quick. That's right. Okay, so redox reactions. Redox reactions, or oxidation reduction reactions, is the second type of reaction that we're going to learn. Remember, the first type is a double replacement, and there are two types of those. But we're going to talk about redox. That's for short for oxidation reduction. All right. So oxidation, when something is oxidized, oxidation means loss of electrons. It means something lost an electron. And reduction is the opposite. It means something gained electrons. Okay? Oil rig. I think on the videos I talk about oil rig. This is how you remember. Oxidation is loss. Reduction is gain. So that's how you remember oxidation is loss. Another way I remember it is oxidation has an O in it, so does the word loss. So if you remember oxidation is loss, then you know that a reduction is gain electrons. So in order to have a redox reaction, you have to have something that oxidizes and something that gets reduced. You can't just have something that oxidizes, because the thing that is getting reduced causes the oxidation. The thing that's getting oxidized causes a reduction. You kind of have to have them both happening at the same time. Okay, so here's a reaction where they're showing zinc metal reacts with copper sulfate, copper 2 sulfate. All right, and so zinc is a metal, so it's a solid. What happens is these basically replace each other. All right, so the zinc is a solid. Anytime you have the element, it always has a zero charge. I'm sure I'll talk about this in a later slide, but I just want to remind you that anytime you have an element, it has a zero charge. But in this case, what happens is the zinc loses electrons and it gives it to the copper. So the copper, it becomes a solid, all right, and now has a zero charge. Remember, the copper here has a 2+ charge, and it's gaining 2 electrons from the zinc in order to become a zero charge. And then the zinc loses its 2 electrons and pairs up with the sulfate, and it becomes ionic as a 2+ charge. So my zinc is starting out as a 0, and it's becoming a 2+ charge. So is the zinc losing electrons or is it gaining electrons? All right, the zinc is losing electrons because it's becoming more positive. This kind of sometimes, again, you have to make sure you understand what the charges mean. It's becoming more positive, it's losing electrons, therefore the zinc is being oxidized. All right, the copper is going from a 2+, we're going to put it right here. It's starting out as a 2+, and it's going to a 0. So it's gaining 2 negative particles in order to become 0. So the copper 2+ is being reduced. Okay, so this is different than the previous reaction we learned in the double replacement. In a double replacement, nothing changes charges. Whatever charge it starts out as, that's what it ends as. So it's not a redox. Redox, things start changing their charges. Notice that our sulfate, the sulfurs and the oxygen, stay exactly the same. It starts as a -2 and ends as a -2. So the sulfate is technically called a spectator ion in this case, because it's not changing. Okay? So, here you go. Here's the equation. I didn't realize it was on the next slide. But oxidation number of an element. So here are rules of oxidation. I believe there are 4 rules. Let's talk about all 4 of them. Yeah, they don't really show it to you the way in class. How I do it is I actually go through all the 4 rules. Here are the first 2. The first one is the oxidation number of any element is always 0. So let's talk about oxidation number. So up until now, I have been calling things that has a charge on it a charge, right? Like sodium has a +1 charge, or whatever. Iron has a 3+ charge, or sulfate has a 2- charge. Well, in reality, these are oxidation numbers. All right. In this case, this word oxidation, it does not mean the loss of electrons. It's the same word, but it means something else. All right. Isn't that like a homonym? Doesn't a homonym mean they sound the same, but they don't mean the same thing? So it's the same thing here. Oxidation in this slide means loss of electrons, but an oxidation number is the same thing as a charge, the element, a charge of an element. So you can either say sodium has a +1 charge, or you can say sodium has an oxidation of +1, or an oxidative number of +1. All right, so that's how you use the word oxidation number. Okay. Now, if you're talking about the element itself, so if you're talking about a hunk of iron, all right, it has an oxidation number of 0, meaning it has a charge of 0. All right. If I have a hunk of sodium, it has a 0 charge. When it becomes ionic, that's when it becomes a +1 charge. So sodium loses 1 electron in order to become a +1 charge. But if we talk about the elemental state, or in the element, like in this example, zinc right here, you see how zinc is a solid? It's the element zinc. So that's why it had a 0 charge. But the copper sulfate is ionic. It was aqueous. It was all dissolved in the water. So it has the +2 charge. It's not in the elemental state. All right, and then you also have to remember the diatomic molecules. You guys remember the diatomic molecules? The have no fear of ice cold beer. Have no fear of ice cold beer. There you go, hydrogen, nitrogen. These are the elemental states for the diatomic molecules. So all these also have a 0 charge. Okay, so if you're talking about the element just by itself, no charges, non-ionic, in the solid or the liquid form, whatever the element is, it has a 0 oxidation state or oxidation number. Okay. Rule 2, so again, there are 4 rules. I'm going to go over all of them. The second rule is the oxidation number in any chemical species. Actually, you know what? I give this differently to you in class. You know what we're going to do? We are going to pretend this is class. I'm going to give it to you like this. Okay, so the first one, elemental state. Oxidations are always 0. Okay, that we have just talked about. Okay, the oxidation numbers of any monatomic ion is the charges we already learned. So, what does this mean? If I have a sodium ion, so monatomic, remember, means only one atom in the ion. What charge does sodium always form? It always forms a +1 charge. So sodium always has an oxidation number of +1 in the ionic form, if it's ionic. Okay? So the oxidation numbers of any monatomic ion is the charge that we've already learned. So calcium is in the 2A row. What's the oxidation number of calcium? It's always a 2+. All right? Fluorine is in the 7A row. What's the oxidation of fluorine? It's a -1. Okay? This is, we already know this. This is not something that you have to relearn. This might be new, but this should not be new. Okay? I'm sorry, that should be fluorine, not Fe. All right, iron. What are the 2 oxidation numbers for ion? We learned about there's a 3+ and there's a 2+. Those are 2 possible oxidation numbers. Remember, monatomic. Nothing new here. You should already know this. All right, that's the second rule of oxidation. So if I have a formula like, I don't know, NaF, all right, the oxidation numbers of the sodium is a +1, and the oxidation number of the fluorine is a -1. Okay? Any questions? That should not be new. That should be stuff you already know. There shouldn't be anything tricky there. All right, the third rule, let me grab my notes real quick. The third rule was that other chart that they showed, but I want to write exactly what I've learned. Okay. All right, so the third rule is, and right now you might not understand where it comes from, but when we go to rule 4, then things will make sense. So this is ions. Okay, a fluoride ion always has a -1 charge. Fluorine would never have anything other than a -1 charge, unless it's the elemental state. And if you want to type in the chat box, what does fluorine in the elemental state? What's the oxidation number of fluorine in the elemental state? 0. Good. Very good. Exactly. So that's rule 1. The fluorine in the elemental state, remember, F2. That's fluorine in the elemental state because it's a diatomic molecule. It's the fear of the have no fear of ice cold beer. All right. Oxygen always has a -2. Always. Unless it's the elemental state, then it has a 0. And hydrogen can either have a +1, which most of the times will have a +1, but it could also have a -1. Okay? Unless, again, it's in the elemental state, then it'll have a 0 charge. Okay, so why is this important? Well, here's the thing. If we look at a sulfate ion, let's look at sulfate, because now what we're looking at is polyatomic ions. Sulfate has a -2 oxidation. All right? Have you ever wondered why it's a -2? Like, where's that -2 come from? You remember the second week of class, third week of class, whatever? I give you a polyatomic charge sheet and said, there you go, sulfate has a -2, and everyone just kind of accepted it because I'm telling you that. All right, well, now we're going to learn why it's a -2. All right, this is for polyatomics. So this is rule 4, all right, for polyatomics. All right, polyatomics, the sum of the oxidation numbers must equal the overall charge. The sum of the oxidation numbers must equal the overall charge. So, what does that mean? All right, if I look at sulfate, that means the oxidation number of sulfur plus the oxidation number of all of the oxygens. I have 4 of them, so I'll just put plus oxygen, plus oxygen, plus oxygen, plus oxygen, must equal -2. Okay, so the sum of the oxidation numbers of my sulfate, so the sum of this plus the sum of all 4 of these, must equal -2. Okay? Now, when atoms, like sulfur, is in a polyatomic ion, they don't have the charge that we learned when you look at a monatomic charge. So we learned that sulfur, as a monatomic ion, has a 2- charge. Well, in this case, in the polyatomic form, it does not have a -2 charge. It can have a +2, it can have a +1, it can have a -6, it can have a +6. It can have whatever oxidation number it needs in order to make this ion. So part 4 is where we figure out what these oxidation numbers are, and it comes off of this. The sum of the oxidations must equal -2. Okay, well, the thing is how do I figure out what the oxidation is? Well, I have to solve this equation in order to figure out the sulfur. Okay, now, the oxygens, we know what these oxidations are from Rule 3. Rule 3 says that oxygen always has a -2 unless it's an elemental state. Well, in this case, it's not in the elemental state because it's bonded onto a sulfur. So each of these oxygens have a -2 oxidation state because that's what Rule 3 tells me. So 2, 4, 6, 8, so that's -8. So sulfur -8 equals -2. Therefore, my sulfur has a +6 oxidation. So that's the oxidation number on the sulfur. Has a +6. Does everybody see how I got that? We're going to do a few of these problems. I just want to make sure you understand where that's coming from. Sulfur can't have any oxidation. All right? Only in the monatomic form it has a -2. But this is not sulfur in a monatomic ion. Okay, so these are the 4 rules. So if you go back to our slides, they kind of show you these rules. They don't talk about those 2 rules I gave you, the one about oxygen always -2 and the monatomic ion. They go straight to this right here where they say get to it. Oh, whoa. That the oxidation number of a chemical species must sum the overall charge. Okay, so they kind of went straight to that. And all right, and then here is where they kind of talk about it. Fluorine is always a -1. Hydrogen is a +1. It can sometimes be a -2. Oxygen is always a -2. And we won't worry about that one right there for right now. Okay, and that's just kind of a... Okay, so let's do carbonate. I want to do carbonate, CO3. Right, so based off of what we just did, figure out what the oxidation number is of the carbon and figure out the oxidation number of the oxygen. You should already know what the oxidation state is of the oxygen. See if you guys can figure that out. All right, I'm going to put this on pause. I'll give you guys about a minute or so. All right, so oxygen has a -2. That we already know. All right, so the carbon is going to have, let's see, carbon plus 3 times my oxygen must equal -2. So carbon minus 6 equals -2. So if you do carbon should equal to +4. Make sure you write the plus, okay? Because it's a +4. The answer is not 4. The answer is +4 because you're showing that you lost electrons. Okay? That makes sense? Let's do a bunch of these. I want you guys to really get good at this. It can be a little confusing at times. So let's do that. All right, let's put these up here. Let's do phosphates. Let's do ClO2 minus. Let's do a ClO2 plus. And let's do SF3 2 minus. All right, so find the oxidation of the phosphorus, the oxygen, the chlorine, the oxygen, the chlorine, oxygen, and the sulfur and the fluorine. All right? Then again, let me know when you guys are done in the box. All right? Oh, Holly and Kayla, I was waiting for you to be done already. You guys aren't done yet? All right, I'm going to go on. I thought you were about to say done. I would have been laughing. Like, oh yeah, I'm done. Yeah, funny. All right, I'll let you guys work on that for a little bit. Okay, let's go over this. So oxygen, -2. I can do this without even... It's always -2. And fluorine, remember, is always -1. All right, so for the phosphorus, it'll be phosphorus -8 equals -3. So the phosphorus will be a +5. Okay? If you have a question, either say question or turn off your mic, or turn on your mic, and I can answer it. For the chlorine, it's chlorine -4 equals -1. So the chlorine will be a +3. Right? In this case, it's chlorine -4 equals +1. So in this case, your chlorine has a +5. And then sulfur -3 equals -2, so sulfur equals +1. Any questions? Okay, cool. All right, so just to kind of show you how this all works together. So again, this shouldn't be anything new, these equations, because you remember when we learned about if you take, I don't know, formula Na2S, right? The overall charge on here has to equal 0, right? So like our sodium has a +1. And the sulfur has a 2 minus. Well, I need 2 of the sodiums, 2 of the +1s, in order to cancel out our -2. So not only, so we learned about it here in the formula, but you can also do it for each of the ions. So if you have a formula, let's say KNO3, for example, okay, what you're going to have to do is figure out what the oxidation states are for each atom in this case. Okay, so the potassium I know is a +1, right? Because the potassium is a monatomic ion. It's in the 1A row. It has a +1 charge. So now I have to figure out what the oxidation state is for my NO3. And my nitrate is a -1 charge. Well, I know my oxygen is a -2. That I always know. All right? However, I'm going to use that now and use this principle to figure out my nitrogen. So my nitrogen should be a +5. All right? And we get it again. Nitrogen -6 equals -1. So nitrogen equals a +5. Okay? So in this chapter, we're going to have to find the oxidation states of each atom individually. All right? So now you know how to find the nitrogen. You know nitrogen has a -3, but that's if it's a monatomic. It's not monatomic in this case. If it's part of a polyatomic ion, you have to kind of do this trick. Okay? All right. And also, if you notice, my potassium is a +1, my nitrogen is a +5. Each of these is a -6. All right. If I add all of these up all together, I should get the overall charge of the whole entire thing, which the whole entire thing has an overall charge of 0, which is what I get. +1 + 5 equals +6 minus 6, 2, 4, 6. So that works as well. Okay. So if you wanted to, another way of doing it for this one would be you can do potassium plus nitrogen plus 3 oxygens all equals 0, right? Because I have a 0 overall charge. So we know potassium is a +1 plus nitrogen -6 equals 0. So my nitrogen has to equal a +5. That's another way of doing it if you have the whole entire formula. If you're just given an ion, then it's the same thing. You just make it equal of the actual charge on your ion. All right?
Steve,
yes.
How do we know potassium is +1?
Because it's in the 1A row.
Oh, okay.
It's a monatomic. Yeah, it's monatomic. Yeah. So all those rules that we've learned still apply. It's really the only new rules is really for a polyatomic ion. It's really that's the only thing that you really have that's new here. If it's elemental, also it's 0. That I know I talked about, but it might not have been important at the time, but it's important now. And then if it's monatomic, whatever charge that we learned back in week 2 and how we found that still applies. So if it's in the if it's in 1A, it has a +1. If it's 2A, it has a +2, and so forth and so on. All right.
Okay.
All right. Cool. All right. This just kind of okay. These now are the types of the types of redox reactions that we have. All right. Let me just look at my notes real quick just to make sure I got that. And then it's types of reactions, and then we do practice problems. All right, so we're actually almost done, and then we got to do one of those. Okay. All right, so there are 4 types of redox reactions. One of them, which we already talked about, is a single replacement reaction. That's the one with the zinc that we looked at the very beginning. So what a single replacement reaction, I'll just give you a generic reaction. A plus BC equals B plus AC. So basically the A replaced the B. Oh. Another way that it could be is A plus BC. In this case, the A replaces the C. So in that case, you get C plus BA. Okay, so it just depends on what A is. If A is a metal, all right, it's going to replace the metal, right? Let's say we have like F2 plus NaCl, right? Well, fluorine is a non-metal. It's going to replace the non-metal. Okay, so so fluorine is a non-metal, it always forms an ion. Okay, so if it forms, an anion, a negative charge, so it's going to replace the element that also forms a negative charge. So in this case, my answer will be Cl2 plus NaF. Okay? Yeah, it's supposed to be enough. Okay, over here, my metal replaced my metal. So the zinc and the sulfate now pair up to form zinc sulfate. And notice these charges. This is what we were doing. The zinc has a +2. The oxygen has a -2. The sulfur has a +6. Right? So all this stuff, if you're thinking about what is this stuff here, it's the stuff that we just learned. And the copper is in the elemental state. That's why it has a 0 charge. Over here, the zinc is in elemental state, has a 0 charge. All right, so that's a single replacement reaction. This is actually how a battery works. This is how batteries work. I know I talked about this in class. I can't believe it was the week before spring break or the 2 weeks before spring break. I talked about a battery where basically how a battery works is this reaction is a spontaneous reaction. It means it happens on its own. And the electrons from the zinc are flowing into the copper, and I have this flow of electrons. And eventually our battery dies because I formed this. And then in order to recharge the battery, I plug this in and I force electrons into this. Where here, electrons are coming out. Here I force electrons in and I cause the reaction to actually go in the reverse direction. So when I plug it in and it starts charging it, I'm pumping electrons into here. I pump electrons into the copper. I pump them into the zinc, which then causes a loss of electrons in the copper. And then I reform this, and then after it's charged, I unplug it, and then this goes that way again because it's a spontaneous reaction. And then eventually I have to charge it again, and so forth and so on. All right. So if you see, there's usually like a zinc and a cadmium battery. All right. Our metal here is cadmium, and the metal here is zinc. That's basically how that works. So usually batteries are two metals, and it's because one of the metals is in the elemental state. All right, I don't know how much more red I can write around this thing. It's getting a little crazy in there. But one of the metals is in the elemental state, and the other metal is in the ionic state. All right. Have you guys heard of a lead-acid battery? Lead-acid? This is the battery in our cars, a huge, gigantic battery in our car. All right. The lead is obviously the metal. So our poles, like the two poles on the battery. So if you have your car battery, and you have a pole here and a pole here, right? These are lead and iron and stuff like that. But we also have these plates inside of the battery, which you don't see. All right? These plates are made of lead as well. And then it's filled with acid. So we've got lead as our solid. Lead is Pb. And then we have, I believe it's sulfuric acid. And basically what happens is the lead replaces the acid, and you actually form hydrogen gas, a little bit of hydrogen gas, and you form that lead sulfate. I can't do that. And lead sulfate is a precipitate. It's not aqueous because it has lead. Oh, actually, it's a 2, so you don't have that. It's a white solid. So if you ever look on the poles of your battery, you usually see all this white crusty stuff all over it. That is, the lead sulfate is precipitating out. So, they say that if you ever have issues with your battery, and it's a relatively new battery, it's to clean off all that white stuff off of there, or to take the lead and move it in order to crack all that white stuff. And if you clean it up, it usually helps in a lot of cases.
So the battery,
I'm sorry.
This is Kimberly.
Yep, hey Kim.
The battery acid is sulfate?
Yep, it's sulfuric acid. Yep. That's why they
I'm
say...
just thinking about my allergy, like, is all sulfate all of them acids, or?
I'm sorry, what? Are what all acids?
Are all sulfates considered acids?
Nope. So,
Just that one.
yeah, what makes an acid, remember, is
yeah,
the hydrogen, right? Yep. Okay, a second type of redox is a combination reaction. When you have two things in the elemental state, notice I have two things in the elemental, nitrogen and hydrogen, they'll have 0, and then they come all together in order to form a compound. So if you guys remember, in the rocket lab, we had hydrogen gas plus oxygen gas, and they came together to form water. That's an oxidation. And again, the way you know that you have an oxidation is that you are changing charges. You're starting as a 0 charge here, and it's becoming a -3. So what's happening with the nitrogen? Is the nitrogen being oxidized, or is it being reduced? So we're going from a 0 to a -3. So is that gaining electrons or losing electrons? You guys want to type it. G for gain or L for lose? You guys want to type it in the chat. Guys, don't do it all at once. It's too fast. I can't read it. So 0 to -3. Does that mean I don't know? All right. So Jacob says gain. Holly says gain. Kimberly says yes. I don't know. Okay. So, well, if it's going from a 0 to a -3, and remember, electrons have minus charges. So if I'm becoming more negative, what's happening? Is it gaining negative things, or is it losing negative things? It's gaining, exactly. So remember, redox means, reduction means gain of electrons. Oxidation means loss of electrons. This is going back to what we talked about at the start, the oil rig concept. So since it's becoming more negative, it's gaining electrons. Gain is reduction. My hydrogen is going from 0 to a +1. All right, so it's going from 0 to a +1. So is that gaining electrons or losing electrons? Well, we're losing electrons because it's becoming more positive. Therefore, the hydrogen is being oxidized. So we have a redox reaction. Here, hydrogen, what's the oxidation of H2? I want to type it in. What's the oxidation of H2? 0, right, because it's elemental state. How about the oxygen, the O2? It's also 0. Right, what's the charge on the hydrogen over here? So hydrogen, it becomes a monatomic ion. What charge does hydrogen always form? Positive, right? Positive what, Jacob? You're right. Positive. What is that? What does hydrogen always become? Hydrogen is in the 1A row. So what charge does hydrogen become? +1. Right, good. And what does the oxygen become? What charge does oxygen always have? -2, exactly. So my hydrogen is going from a 0 to a +1. So is that oxidation or reduction? So either put O or R. O for oxidation, R for reduction. So is it losing electrons or gaining electrons? What does everybody think? You just make a guess. Oxidation? Yep, oxidation, exactly, because it's losing an electron. So I'm losing electrons. So hydrogen is being oxidized. Usually you put like a little bracket over it. And the oxygen is going from a 0 to a -2. So it's gaining 2 electrons. So that will be reduction. Exactly. So kind of showing you how everything in this chapter now in the second half all comes together. So I can give you a chemical equation, and you can figure out what the oxidation states are for each side, and then figure out what's happening to it. Is it oxidizing or is it reducing? All right, another example is a decomposition reaction, which is the opposite of a combination. In this case, I bring things all together to form a new compound. Here I have a compound, and I'm breaking them apart into the individual components. Okay. So in this case, sodium and hydride. I have a H- in this case because the sodium has to have a plus charge. And then sodium in its elemental state will have a 0 charge, and hydrogen, remember, in the diatomic state becomes H2. because that is the elemental state. And we're going from a -1 for the hydride to a 0. By the way, H- is called hydride. So -1 to 0, it is losing an electron in that case, right? It's becoming less negative. So that means it has to be losing a negative electron is coming out of it. So therefore, the hydrogen is being oxidized. And then what's our sodium doing? Plus to a 0. It's gaining an electron. Because +1 minus an electron, here's the electron, equals 0. So it becomes 0. So therefore, the sodium is being reduced. So it's gaining electrons. All right, and we're going to do these types of equations right after I talk about the fourth type of chemical reaction. So if you're kind of like, kind of getting it, don't worry. We're going to do some of these for practice so that you guys got it. Finally, the last type of reaction, which it does not use the electrons and all that stuff, is called the combustion reaction. Combustion is where you have some sort of hydrocarbon. This is a hydrocarbon because it's carbons and hydrogens, so we call it a hydrocarbon. And you add it, so usually it's a certain amount of them. And then you add it to oxygen, and you always form carbon dioxide and water. That's how you know it's a combustion reaction. All right, and you can kind of see where this, I believe, should be that right there should be a -4, not a +4. I mean, an error in the slide. I don't think I can change it. Let me see if I can change it. No, I can't change those. That's actually a photo. But in case you're confused by that, that should be a -4. Okay, so that's a combustion where you have some sort of hydrocarbon plus oxygen gives you CO2 and water, and your carbon is always the one that is being oxidized. All right, notice it loses electrons, -4 to a +4. All right, and then your oxygen is the one that's being reduced in these, always. The hydrogen is not doing anything. Oxygen is going from 0 to a -. So it's gaining electrons. Okay, another combustion that you can see, I'll show you other ones, is rather than just having carbons and hydrogens, you can also have an oxygen attached to it. You can also have a nitrogen attached to it, or you can have a sulfur attached to it. And in all these cases, they still react with oxygen. And you still form a CO2 and water. If you have a nitrogen, though, you form CO2 and water, but you also form NO2. And then for sulfur, CO2 and water, but in this case, SO2 as well. Okay, so if you have anything other than oxygen or hydrogen, you also form the corresponding oxide of that element. Okay, so if you ever see these. So I want to talk about this because this we kind of is in our, believe it or not, our everyday lives. There is a compound called Dimethyl Sulfide. This is the structure of dimethyl sulfide. All right, I'm going to just write it out in formula form. Oh, there shouldn't be a plus there. That's plus O2 forms CO2 plus water plus SO2. This compound, dimethyl sulfide, is put into our natural gas. Okay, natural gas is a combination of this is methane. Sorry about that thing that happens all the time. And I think a little bit of ethane as well. This is ethane. I think some propane as well, which is 3 carbons, but these are kind of the major components of it. Believe it or not, these have no odor at all. They have 0 odor. You can't see it, you can't smell it, you can't feel it, you can't hear it, nothing. If it's completely pure, okay? It has no odor or anything. However, we know when we have a gas leak because you can smell it. All right. The reason is because the gas company puts a very small amount of this compound in there. Any compound that has a sulfur and carbons attached to it usually has a rotten egg smell. Has a really nasty smell. All right, it has a very sharp smell. It's a rotten egg smell. Skunk odor. This is the structure of skunk odor. It's not important that you know it, but just to give you an idea. There's a bunch of carbons on it, but it has a sulfur. All right, so this is the main odor in skunk. But if you notice, it has a sulfur. Usually things that have sulfurs and carbons and hydrogens have that rotten, eggy smell to it, or a skunk smell to it. And our noses are very sensitive of these sulfur molecules. We can smell very, very small amounts of this. Okay, so the gas company, when they have all their methane and ethane, they put in a very small amount of this in there. Well, when it burns it normally, what happens is it turns into CO2, water, and SO2. SO2, we can't smell this. This has no odor. Okay? Or has a very faint odor that our noses aren't able to smell. But when it doesn't burn it, so if you have a gas leak, I obviously am not combusting this. So then I have a whole bunch of this, along with all the methane and ethane in the air. My nose is able to actually smell this now, and I can smell it. But when it gets burned, it turns into SO2, and I can't smell it. All right? So that's how our gas works, and I just want to give you an actual example of this. All right, can you guys hold on 1 second? All right, sorry about that. Okay, so I just want to give you a real-life example of this oxidation, just to kind of show you where it applies to us. Okay. Sample problems. You know what? Let's do one of these. What does it say? Determine whether you should find. Okay, so we're going to go a little bit more into depth into this. So let's take this compound right here, this calcium carbonate. All right. What I want you to do is, first of all, try to figure out which of the four reactions this is. Is it a combination? Is it decomposition? A combustion? Or it didn't put here a single replacement reaction. I don't know why they didn't have single replacement. Okay. Then, additionally, I want you to figure out which atoms are being oxidized and which atoms are being reduced. Okay? So again, it goes back to looking at the charges of each of them. So the calcium has a charge, and then it has a different charge on this side, and you have to try to figure out, is it changing its charge on each side, or is it the same? If it's the same, then it's a spectator ion. It's not being oxidized or reduced. Okay? Just so you know, every equation has to have one being oxidized and one have to be reduced. Okay? So let me actually put this on a different. Oh, sorry, I didn't mean to mute myself. So let's actually know what we can do. Let's be able to copy and paste it over. All right, so when you're done, just put that you're done in the chat box, and we'll proceed from there. And just how much time we have left after that. No one has said they're done. What's going on, guys? Or have they? Maybe I'm having issues with my chat. Oh, yeah, there we go. Never mind. Got it. Only a few people. All right, let's go over it. Okay, so first thing was, what type of reaction is this? Is actually a type of decomposition reaction. Notice we're going from one compound and it's breaking it apart into other compounds. So this is a type of decomposition. All right. All right. Now, as far as your charges, so if you look at calcium carbonate, calcium has a 2+ charge because it's in the 2A row, and then we have it. So if you look at this, it's a calcium, and then it's a carbonate. All right. So now I got to figure out what the charges are on my carbon and oxygen. Well, oxygen is always a -2, so that I always know. So carbon -6 equals -2, so this carbon is going to have a +4. So this carbon on this side has a +4 oxidation. If you go to the other side, calcium oxide, calcium has a 2+ charge, oxygen has a -2 charge. That's pretty much it. +2, -2. So it's calcium oxide. It's just how we've learned. Carbon dioxide, all right, oxygen is always a -2, so carbon -4. In this case, my overall charge here is a 0, equals 0. So my carbon also has a +4. All right. Something go wrong here? I'm sorry. Yeah, that should be +4. You know what? This example is not a good example. Because maybe that's why people weren't ready. The carbon should be changing its oxidation. I don't know why it's not changing its oxidation. Did I do this right? Yeah, that should. So, I'm going to have to look at this one because this one technically should be changing. Nothing is changing, which is weird. I don't know why it's not changing. Sorry about that, guys. That was a bad example. But it is a type of a decomposition reaction. Usually in oxidations you have changes. All right, good. Yeah, you shouldn't be the only one. Yeah, usually you have changes in oxidation. So this technically is not a type of redox reaction. Once again, your publisher did something that is not totally correct. I mean, it is a type of a decomposition reaction, but it's not a redox, which they should not be doing that. I mean, those do exist. You can have a decomposition without being a redox, but usually you do. Let's actually do one where I know actually has an answer. So sorry about that.
That's why I just said I was ready.
Just automatically. All right, let's do this one. Let's do Fe2O3 plus CO forms Fe plus CO2. Okay, so in this case, tell me what is being oxidized and tell me what's being reduced. You don't have to tell me what type of reaction it is. Okay, just tell me what's being oxidized and what is being reduced. That one I know should work, or is a redox reaction. All right, I'll give you guys a few minutes. All right, so iron here has a +3, oxygen's a -2. The oxygen here is a -2, and the carbon here is a +2. Here, the iron is a 0. So the iron is going from a +3 to a 0, so it's gaining electrons, therefore it's being reduced. So the one that's being reduced, there are two ways to answer this question. You can either say it's the iron 3+, or you can say it's the Fe2O3. All right? You never say the product. The product is never the answer because that's the outcome of the oxidation and the redox reaction. Okay, so the answer is never Fe0 or CO2. Don't put this as the answer. Don't say iron. Because are you talking about this iron or are you talking about this iron? I want you to be very specific as to which one of these is your answer. So either say the Fe3+ is being reduced or you just mention the whole entire molecule. Okay, and on this side we have a -2 and the carbon here is a +4. So this carbon is gaining electrons. I'm sorry, is losing electrons. It's going from a +2 to a +4. So that is being oxidized. So either you put the C +2 or you can put CO. Okay, so these are what's called half reactions, where you say 3+ to Fe0. It's the half reaction. Or you say C +2 to the carbon +4. Okay? Does that make sense? Everybody get that? Okay, so that's pretty much all we have time for. I definitely want to finish this chapter up tomorrow. I am going to start chapter 11 tomorrow as well, so we can get chapter 11. But I probably have maybe another 10 to 15 minutes on this chapter. And then on Thursday, we'll do a bunch of these problems. So if you're still a little kind of like a little confused, I've only done one problem, but we will do a bunch of these tomorrow. But we definitely will do more on Thursday. All right? Everybody okay?
Yeah, and I just wanted to confirm that the exam date isn't completely set yet.
It is not set. That is correct.
Okay, but we're thinking.
We're thinking the end of next week or the beginning of the week after.
Okay.
All right. Anything else? That's good. Okay. Then I will see you guys tomorrow.
Cool. Thanks, Steve.
Yep, no problem.
Bye.
Bye-bye.